Remember the last time you heated a pan on the stove? The pan expanded, right? That, my friends, is thermal expansion in action. It's a fundamental concept in physics that affects almost everything around us. We've already explored the basics: linear expansion, where objects expand in one dimension, area expansion, where they expand in two dimensions, and volume expansion, where the expansion happens in three dimensions. These concepts are relatively straightforward, but as with anything in the universe, there's always more to discover. Get ready, because today we're going on a journey beyond the basics, into the fascinating world of advanced thermal expansion. So far, we've assumed that objects expand equally in all directions when heated. But what if I told you that's not always the case? Welcome to the fascinating world of anisotropic expansion. Anisotropic expansion occurs when materials expand differently, depending on the direction in which heat is applied. Imagine a piece of wood expanding more along its grain than across it. That's anisotropy. This phenomenon is crucial in materials science and engineering, especially when dealing with materials like wood or composite materials. The formula for anisotropic expansion gets a bit complex, as it involves tensors and directional coefficients of thermal expansion. But the basic idea is that the expansion is no longer uniform and depends on the material's structure and orientation. Cavities within materials also exhibit anisotropic expansion, expanding differently based on the material's properties and the direction of heat application. Imagine a metal rod trapped between two immovable walls. Now heat it up. The rod wants to expand, but the walls say, "No way." The result? Thermal stress. Thermal stress is the internal resistance of a material to changes in volume due to temperature changes. It's like the stress you feel when someone pushes you in one direction and someone else pushes you in the opposite direction. The formula for thermal stress involves Young's modulus, a measure of a material's stiffness, the coefficient of thermal expansion, and the temperature change. Stress sigma equals EAdT, where sigma is the thermal stress, E is Young's modulus, alpha is the coefficient of thermal expansion, and dT is the temperature change. Understanding thermal stress in rigidly fixed bodies is crucial in engineering, as it can lead to material failure if not properly accounted for. Ever notice those gaps in bridges, sidewalks, or railway tracks? Those are expansion joints, and they're not there by accident. They're essential for preventing thermal stress from wreaking havoc on our infrastructure. Expansion joints are designed to absorb the expansion and contraction of materials due to temperature changes. They allow structures to breathe, preventing cracks, buckling, and potential collapses. Calculating the size of expansion joints requires knowing the material's coefficient of thermal expansion, the expected temperature range, and the structure's length. It's a delicate balancing act between providing enough space for expansion and maintaining structural integrity, especially when dealing with cavities and thermal stress. Let's step back and look at some real-world applications of these concepts. Take cavities, for example. These structures rely on precise dimensions to function correctly. But here's the catch: even slight temperature variations can cause these components to expand and contract differently due to anisotropic expansion, distorting their shapes. Engineers have to carefully choose materials and design techniques to minimize these effects. And what about bridges? These engineering marvels are constantly exposed to the elements, experiencing significant temperature swings throughout the year. Expansion joints are strategically placed to accommodate these changes, preventing catastrophic damage. Thermal stress is not just a theoretical concept, it affects our everyday life. It's all around us, often in subtle ways. Remember that glass jar you couldn't open? Try running hot water over the lid. The heat causes the metal lid to expand, relieving the thermal stress and making it easier to twist open. But be careful. Rapid temperature changes can lead to thermal shock, where the stress becomes too much for the material to handle, causing it to crack or shatter. That's why you should never pour boiling water into a cold glass jar. Expansion joints are a symphony of flexibility. These unsung heroes of infrastructure manage thermal stress in cavities. Ingenious engineers design these gaps to withstand the relentless forces of nature. From bridges to buildings, pipelines to railway tracks, expansion joints play a vital role in ensuring our safety and the longevity of our infrastructure. They allow structures to move and breathe in harmony with their environment. Looking to the future, Understanding thermal expansion and stress can lead to innovative engineering solutions. From designing spacecraft that can withstand the extreme temperatures of space, to developing new materials for advanced technologies, the principles we've discussed will continue to shape the future of engineering and innovation. In our concluding chapter, we reflect on the fundamental phenomenon of thermal expansion and stress, and how it expands our understanding of material science. From the intricate world of anisotropic expansion and thermal stress, to the crucial role of expansion joints in our everyday lives, these concepts govern the behavior of materials and underpin countless engineering marvels. As we push the boundaries of science and engineering, our understanding of thermal expansion will continue to evolve, leading to new discoveries and innovative solutions for the challenges of tomorrow.